Yes. So we're pushing forward today with the stuff here. My rebels. This is really cool, by the way. Showcase it to others. You can do that. Okay, quantum mechanics exercise. That's what I was working on. I was working on doing that thing with exercise 2.1, which I probably have to look for it again. And certain systems roadmap. Go to the 2.1, and I was trying to get that done, or to get the first part done, but I'm not sure that I'm doing this correctly. So maybe we should just like kind of print, so you know, kind of do this a bit more like step 1, the probability density, right? So probability density, and then we kind of do print, and we do this part, because that's essentially what it is, right? So it's the thing times its conjugate. A is real, R is real. And I want to get at the same solution, which is this guy here, right? So this is what I want to get. And this is what we have, what we start with, right? Because we need to find n. And we know that R. It's funny because that is not going to depend on A. On R, sorry, on A. My A here is alpha, right? So this is alpha in the exercise. And I'm in Python, so that's this basically. And I'm here, and what I was doing is, I doesn't remember, so, but anyway, I can do Python, I can do that, right? So what is it doing? Okay, so first of all, let's just comment that, make sure that what we do makes sense. So I can zoom in because it's not a lot of big code. So what we're doing is, does this make sense, right? So we have n times to the, times conjugate n. Yes. That makes sense, because what we're doing is these times, and then we know it's real. So if we know it's real, then we know these things are real, so we know the conjugate is the same. And so we just get like a 2 here, right? But why times conjugate n? Yeah, of course. Okay, because n, we don't know. We don't know if n, that's the thing, right? I mean, n can be complex, right? N can be complex, definitely, or maybe not. The problem doesn't tell us. Factor n. Of course it can be complex. That's the whole point, right? It's an amplitude, right? So, oh, give me a second. So I think that seems to make sense so far. Let's maybe again try to, and I did that last time, but let's try this once more, also by hand here, if that works well, because last time it didn't work really well with my pen. No, that works well. So we have n, and then we have nothing. So what we have n times e minus alpha r. And so what we're doing is we're doing these times its conjugate. I'll call it star. And so, well, that is basically, that's why this is like n. So we leave the same thing here. Now n is can be complex, so it's a conjugate. And then we know that because these things are real, we know the conjugate is the same. So it stays like that. And that's why these two things add up. And so we have n times this thing times e minus 2 alpha r. So I think that basically makes sense here. Now what we need to do is we need to basically, so the next step, right? So now that we have the conjugate, we need to integrate it. And so we need to integrate it with respect to r, right? So now we need to do basically print step 2, basically have, it's like an indefinite integral with respect to r, right? And so this is basically, what am I doing? So print integrate conjugate. Maybe I should just compute this, and it's like S1, right? So call it S1, and so I print S1, that's step 1, and then we integrate step 1. I'm not so sure, and I have to say with respect to what? So I have to say with respect to R, right? But I don't know what that prints. So let's see. That doesn't solve the integral, does it? Yeah, that's the problem. So here it starts trying to solve this. And that's what bothers me, right? Because, okay, so what is piecewise? Piecewise. So what is piecewise? What do we have? So we have, this is basically Sympy integrate. And then we also want to look for Sympy piecewise. Init printing integrate. So I give it something. So integrate f of x returns the indefinite integral. That is okay. That is what we want. But it's actually going to really integrate that. And integral transforms. We don't care about integral transforms. Laplace transforms, I have no idea what this is for. Whatever. Piecewise. What is the piecewise? Okay, so okay, maybe it's because what it's doing is so it's because I guess what this is I don't know what is it, but it's probably piecewise. So the one is assuming, so we're taking just the real part, and the other one is the complex part, I guess. I don't know what NE is. Because this is what we have. Okay. Yeah, that's one. And then that's like something else, and I don't know what true means. What is piecewise? So Sympy piecewise. Piecewise complex. Can you just, the documentation is really shitty, I have to admit. So, God, what is piecewise? Sympy piecewise. Integral results in piecewise object. Oh, there you go. So in Sympy I have an integral which returns a piecewise object. Integrate. Okay. I would like to extract just the first branch of this piecewise equation. In other words, I would like to be able to do something like part 0, pocket of a bit I've managed to find. In general, R is the correct way to access parts of an expression. In this case, though, there's an option to integrate that will let you ignore convergence conditions. Cons none. Also, if you explicitly set the assumptions that you know on your variables, often the convergence conditions resolve themselves. It doesn't seem to happen in this case for any simple assumptions on Z, though. For example, if you knew that Z was real, usually assuming that things are real or even better positive, then you know it will help a lot in ensuring convergence. But what is that essentially telling us? So what are the things in here? So we have, what is NE? What is NE? Sympy NE object. Don't even get that. So it's like 3 parts, right? So this is one part. And then true. What is true in this case? I want to know the specific interface. Piecewise. It's an expression. Jesus, what is that? Oh. Integrate. Integral. So it's doing something here. Like, what if I assume that n is real, for example? Like, if I do that, like, what do I, like, does that simplify the equation? Probably. You still get this. No, it's a bit different. Okay, yeah, because you get n squared, but but it's still piecewise. So the only thing that changes is that you don't get that and conjugate kind of thing. Like if I do like, I think, I don't know if that's just the way that it's, yeah, I assume that it's implicit. Minus infinite to infinite. Poof, okay. Oh, look at these. Actually, we're getting something here. We're getting something here. We're getting pi and a half, and what the fuck is that? Zero. So first of all, why? Can pass multiple limit tuples to perform a multiple integral. For example, to compute. Okay, no, that is the upper limit, lower limit. So note that in Sympy does not include the constant of integration. If you wanted, you can add one yourself or rephrase your problem as a differential equation and use dsolve to solve it, which does add the constant. The compute a definite integral pass the argument. For example, to compute these, you would do. Okay, so actually you have to add these minuses. And if you don't, what happens? Then you don't, then it's indefinite, right? Well, there's a difference between being indefinite and then minus infinite and plus infinite, I guess. It actually makes a difference. But okay, what are we getting? So we're getting 0 and we're getting like, I have, whoa. What is arg? What is arg? Sympy. What is arg? Can I not just... Okay, real arg. It's just arg. That's not what I mean. I mean arg. Arg. It is impossible to find anything. How can I know what the heck is arc? So what this is telling me is the absolute value of something, or smaller than pi, but I just don't know what that expression is. I just don't know what that expression is. Cannot these print it nicely? I think I like Sympy print options, print expressions. Sympy import, import, import. What is srepr? P print, okay. Let's try that. Let's try that. Okay, interesting. Whoa. Okay. Okay. So, now I get it. Okay, so it's 0. So it's 0 for this case and that otherwise. So if arc a, whatever that is, plus pi is more than pi and a half, and then the absolute value of arc a is more than pi and a half, then we get that stuff 0. Now what we're looking for is we're looking for these, you know, these minus 1, I guess. The n conjugate. Essentially, what we're looking for, we're looking for saying, cool, so that integral. So if that integral, so I'll say that is basically S2 is that thing. And now we're saying, well, S3 is like equals that integral minus 1. And so what we're doing is solve for n, right? Solve for n, and so now we're doing p print S3 because we want to find the n that makes, you know, that equation equal to 1. Boom. What's going on here? Invalid non-comparison. Where? Not a number. S2. Y. Line 19. I think no, that's correct. Okay, no, that is correct. That should be correct. If I don't add these infinites, what does it do then? What does it do then? Oh, interesting. Huh? Okay, but it doesn't print S3 or what? Yeah, it does, but I haven't. Step 3. Solve for n. So S2 equals 1, right? Let's see what that gives us. Okay. that actually works if I don't add these infinites. But I want to solve for n. That's not solving for n. I want to solve n. So what do I have? So Sympy solve. So let's say you have that, and then what? Solve x, y, and that should actually print this stuff like that. Solve for n. So solving for n, and n is like, you know, it just can't be like that, like recursive or something. So if I add back the these, then it breaks. Solve breaks, invalid non-comparison. Yeah. This is from last year. Integral. Complicated. What am I getting here? Okay, but I've gotten a bit farther than before, than last time. The problem is that it's 0 in these cases. The problem is that it gives this kind of piecewise shit here. Whereas like, well, do we know, so alpha is a real parameter, or like R is just, you know, complex conjugate for these. Oof. Oof, oof, oof. Does this make a change if we add n being real? I don't think so. That also breaks. Solve for n. The fucker, man. It should be something pretty simple, shouldn't it? And I don't think I'm doing anything wrong here. but it's just saying piecewise invalid non-comparison. Come on. From let's try something. So because this is a function of r, if r is a radius, like the radius shouldn't be negative, right? It's like we could do that from 0 to infinite. Maybe that's a better thing to do. It seems to be a function of the radius, right? So this will just be, it's not telling us anyway. I mean, here just telling us about the momentum, something being isotropic and whatever. But what if we would just say, like, let's see how that changes. So if I go from 0 to infinite, because maybe that makes it. What? Well, we should put a 0, not an O. Ah, come on, it also breaks. But that looks a bit better. N squared. If whatever arg A is below pi 2, yeah, okay, because then otherwise what? I don't know. But it can't be, that's step 2. That's what the integral would be. Okay, but in this case, what if I know, if I know that's real now, how does this change the story? Because that, okay, so that kind of, there's something here. There's something here, definitely. Let's take a look at the exercise announcement again, or the solution actually. So look at these. So it's actually n equals something. It's a cube, man. A cube. Where the fuck do I take that? Am I doing normalization well? That's the first question. So quantum mechanics, quantum example. How to normalize a wave function in quantum mechanics. Maybe that's going to help us speak. Whoa.
This video is going to serve as an introduction to normalizing a wave function. So recall that we interpret...
Okay, so we're doing that correctly. I'm doing that correctly. It's minus infinite. So
the modulus square of the wave function that is vertical. The density I have particle in a box. This is the n equals 2 state for the particle in the box, and for simplicity I've chosen the box length of L equals 1, which makes the L from our wave functions disappear. And so an unnormalized version of the wave function might be like this, where it's just psi of x is equal to sine 2 pi x. A normal is the only difference is the height, or the amp length of the box. What's normalized? This function, multiply it by its complex conjugate, and integrate over all. So we're going to look at this in two ways. First, we're going to take in a case where we're just going to wave from let it go. So
okay, so what do we do here? Is it normalized? And so you do that. It's gonna, okay, so oh, what? Let's return to our n equals 2 state for the particle in the box of length 1. Is it normalized? So why? from 0 to 1. Okay. I don't get that though. Why are we changing the frames here?
Normalized wave function has this form, psi of x equals sine 2 pi x. So we're going to go ahead and check if this is normalized. So we're going to plug that psi into our general expression for psi star psi integrated over all space. So you can see I plugged in psi squared.
So the function, is that the example? I guess so. Okay, just because the example goes from 0 to 1, I guess that's...
So the integral is to show how we sort of make this expression. Go ahead and check star psi.
Okay, fine, whatever.
Want to normalize this, we're going to go.
So we multiply the wave function by a constant a. And so now we do these, right? Yeah. And so, I mean, that is it's simple, right? It's simple. The thing is,
go ahead and take this wave function and we're going to multiply it by a constant a in front. That's going to be a times sine 2 pi x. And now we want to try and find what value of a makes this wave function normalized. That is, that makes this integral here.
maybe there's just a smarter way that I can formulate that that integral. You know what I mean? What if I, and I'll just probably spend 4 more minutes on this because I don't have time, but what if let's just take the n, right? Let's just plot that. And what was that? Desmos. So it's just Desmos graph. Whatever. There we go. So we'll just take e to the minus. We'll just take e to the minus. You know, let's just say. Whatever, like 3 times 3x, right? Okay. So what happens if we increase this, like 4, 7? This is a real number, right? Yeah, that's the problem, right? The problem is that this integral is how am I supposed to integrate that, right? I mean, the integral, like if I don't put any bounds to these, integral of minus x is something like that. And so if I just add here, I'll just make it more inclined, right? 0 is just the whole thing like that. And so we know this is a real parameter, right? So it just must be something like that, and then it just behaves like these. And so okay, so what it does is it kind of moves these a bit here. But I mean, the integral, I need to make it a bit bound. There's something off here that I need to do that I don't know how, because that is, this function just goes nuts. You know what I mean? That's why it's so weird. Like, how can I make sure? Maybe I just have to, yeah, maybe that's why maybe I have to just do 0, right? Because it's a radius what we're doing. So I'm taking a look at the area in here. So I think I definitely have to do 0. Otherwise it just makes no sense. So I'm sure that I'm quite convinced that I have to use 0. So that I have to just say, well, n doesn't have to be, it can be complex, but I'm pretty much sure that I have to call that this has to be 0. Cool, I don't know, we'll take it there, but I think I've done a bit of a one step forward at least. Because that still tells me, that still gives me an error, but at least it gives me these. What if I just say, let's say 2 or 3 or something like that? Oh, look at these. So these numbers, no, okay, forget about that. Where is the area where this is kind of 2? Yeah. Like if I just do like say 10, right? I'm just playing with these. Let's just put some limits to these. Okay, we're getting something. Okay, we're getting something. Minus 20. Okay, that's something that's better. It's not breaking. Maybe it's just really about these. What if I just say A? It makes I don't know. It just makes no sense. But it seems like if I okay, we're getting somewhere. For A, okay, we're getting somewhere. I don't know. It's definitely not good, but it's something. Okay, something along these lines. So I just got to figure out a way to constrain that integral to make it easier. There has to be something that I can use to make that easier, because otherwise I can't just equal that 1 because it's infinite, right? I mean, that just goes on forever. So I gotta bound it somehow. I'm assuming I'm getting, I mean, what if I add, okay, so what happens with these here? Okay, that actually moves the thing up. Or down. Okay, interesting. So that's the parameter we're looking for. It kind of moves the thing up, and the other one kind of opens up the curve. Something like these. I just don't know what's the smart way to go about these. So, and what is the the logic behind these? Anyway, see you next time.